Hi everyone, welcome back to my channel. My name is Cha-Cha, and today I'm going to be talking about gases. Specifically for the MCAT, I'm going to be talking about ideal gases. And then my next video, I'll be talking about like gas analytical techniques, just because I didn't talk about that in my analytical chemistry technique video. But as I realized when I was creating the gas analytical technique video, you should probably learn a little bit more about gases and why they're so important and why these techniques work. Um, so what's the deal with gases to begin with? So they are a fluid. Contrary to common belief, liquids are not the only type of fluid. Gases are also. But the main difference, or one of the main differences between fluids and gases, is that gases are compressible. Um, this is partially due to like the large gaps between the molecules. Um, and gases, whereas liquids, they don't really have as big of gaps. And ideal gases. So we'll get more into that. This is like the bread and butter for the MCAT. They aren't really going to talk to you about non-ideal gases just because that is like really complex and you can't use our favorite equation down here, which is PV equals nRT. But what are ideal gases and what are some assumptions that are made with them? So there's three main ones. So the first thing is that you assume no volume. They are the skinny legends of the chemistry world. So there's no volume with them. You also assume that there's no molecular interactions, partially because like of those large gaps. But if you have molecular interactions, that makes everything a lot more complicated. So like if you have to think about covalent bond, dipole, dipole, just like a lot of the equations that we're going to see don't really work. Then also assume that they're elastic collisions. So what do I mean by elastic collisions? So that there's no kinetic energy lost. So essentially I have like this little thing, right? So it's like they're kind of like rubber bands. They will bounce right on back. They'll be just as dynamic as they were beforehand. So there's no energy lost, which is like obviously that's not this is like theoretical since that's not real. That would violate a lot of the thermodynamic properties. But in the cases of the MCAT and just like basic chemistry, you assume that there's no energy loss. So here I have these like little molecules. The red one is going, oh, since it's going to collide with the green one just at that right angle, where like the collisions can happen, and there should theoretically or like potentially be energy change, but for here there's not. And then they're like, it's the moment of anticipation, and then they go away. They're moving just as fast as when they started. There's no energy transfer between the two of them. They're going on their merry ways, and that was pretty uneventful, is what the green one's saying, because he's just going back the way he came. He thought it was going to be like this whole big thing, life-changing event, and it's just like, eh. eh. Um, so the big one equation that you need to know is that PV equals nRT at standard like so at STP2, which is what you assume like is at 0 degrees Celsius or 273 Kelvin. Um yeah, and then so this is the conversion for between Celsius and Kelvin. And that's kind of like the main thing that you need to know. Um sorry, not is equal to Kelvin. That's like the main temperature conversion that you need to know. There is some for Fahrenheit, but that's not as important between Celsius and Fahrenheit. So how did we get this 22.4? I feel like a lot of the times like people will like say, oh yeah, it's 22.4 liters per mole. It's like, where the hell did you get that number? Because um at least I was always like that. No one really showed me how. Maybe they just assumed that you'd put two and two together, but I was maybe too um like I just didn't realize like so here's the equation. So this is at STP. So like STP2, like so 1 atmosphere or 760 torrs, 760 millimeters of mercury, and around 1 to 10 fifth Pascal. So 1 atmosphere, 760 mmHg, that's the main one. And then approximately 1/10 to fifth Pascal. And pascals are really cool because that is what you can have for your force. Um, like that's important since it could be converted to newtons. I think it's newton squares per meters. Give me 1 second. Yeah, sorry, newtons per meter square. is what a Pascal is equal to. So that's really cool since you could just convert it, right? Um, but to force, so like if you have something that's saying, oh, this force, like since a lot of the times you'll see pressure is equal to force over area. And if you're given a pressure here, you could just use pascals and then convert it since you know it'll be newtons over a meter square. Anyways, I'm getting ahead of myself. So when you plug in 1 atmosphere, times volume, volume is always in liters. And then you have your moles on the side since it's PB, right? Pressure volume equals N R. So like when you're dealing with stuff at STP, your R value, and I'll get more into this later, is always going to be 0.08206 atmospheres times liter over Kelvin times moles. So you have that times 273 Kelvin or 0 degrees Celsius. And then if you plug and chug, so you do 1 times 0.8206 times 273, that's where you get that 22.4 liters. And it's really important if you can only use this at 273 Kelvin, right? Since like that's where you plug and chug. So like if you were to move this at like room temperature, which is like 25 degrees Celsius, um, which is 298 Kelvin, then that's not going to be the same thing. So it's not going to be 22.4 liters per mole. It's going to be something else. But this is just like a common thing. It's just like, and so you don't have to do like these multiplication problems on the MCAT. It's just something useful to keep in mind. A number, magical number in your back pocket. Um, First, let me talk more about the two different R values that you'll come into contact with on the MCAT. So first you have the R, which I already talked about, is a 0.08206, and then you have the atmosphere times liters over Kelvin times mole. And then if you ever forget the units, just think of PV equals nRT, right? So like if you solve for R, then you're going to have your atmosphere times liters on the numerator, and then you're having moles times Kelvin or on the bottom. And just remember, whenever you're looking at that temperature, right? So like T is always going to be in Kelvin, most likely, unless like it'll cancel out some other way. Just assume that. And then these processes, they all use standard STP. So use a 273 Kelvin or 0 degrees Celsius for stuff that just like is PP equals nRT or like just like those theoretical values that like you probably won't come into contact with in real life. That's kind of like the thing. It's like not real life. It's those theoretical type values. And then over here, you have your R for 8.314 times joules over moles times Kelvin. And then this is typically used for like thermodynamics. So it's like anything that has joules. Most likely you're talking about energy, like for entropy or work, gives free energy, stuff like that. And then these procedures, you assume room temperature, 25 degrees Celsius or 298 Kelvin, because it's more practical to assume like energy related processes occur at room temperature, right? And not at freezing, not at that 0 degrees Celsius, because just like when you encounter something, if you're doing an experiment like in a lab or something, like it's not at like there's not snow around, right? Like that's just uncomfortable for the scientists. That's like cruel and unusual, right? Um, Eighth Amendment, hey. But so that's why you assume it's at 25 degrees Celsius, since that's like normal temperature, like that you would encounter like anything just day-to-day life. It's a real life chemistry sort of. That's kind of like what I said earlier, is like you need to recalculate that 22.4 liter rule. It's not accurate, sorry, accurate at room temperature. And then let's go back to the PV equals nRT. So there's three different types and they all have like names that you'll see in the MCAT. So it's kind of important that you know Boyle's versus Charles versus Avogadro's law, just because even though like you're just rearranging the equation and it's really simple to like understand like where it came from, for some reason they just have to attach different like names to it for you to remember. And it can be kind of hard to have the distinction, but it's just something that you need to like route memorize. Um, yeah, and also like when you're looking at like Boyle's and Charles and Avogadro's laws, like for example, for Boyle's law, you're assuming that nRT, those are all constant. So they're not changing, so they'll cancel out, which is what leaves you with PB equals P2, sorry, P1 V1 equals P2 over P2. Um, And how I remember boils, it doesn't, I don't know, B for backwards. So only like the back half of the energy is included. Backward or like the reactants, like you know how you have like usually like you have like deltas, products, minus reactants. I kind of think of the left-hand side as your reactants. Like if you were just to have this as like a forward arrow for reaction instead of like the equal sign. And this is more your product. So it's kind of the backwards of the enthalpy, but the products are constant. So it's just a P1 V1 equals P2 over V2. Sorry if that's like kind of confusing. There's not really one like at least I don't really have a mnemonic for Boyle's law, but if you have one, please feel free to drop it in the chat. Just because I'll use it for sure, and then it might be helpful for other people. And then Charles' law. So this is V1 over T1 equals V2 over T2. So for this one, right, you're assuming that the pressure is constant, then moles are constant, and R, since R is always going to be the same no matter what, that's a constant regardless. That's going to cancel as well. Um, so what I like to think about is like the Celsius, like the drink. So the drink takes up like or like the temperature, but that can kind of get confusing. Like Celsius is related to temperature as well. Um, and like Celsius themselves, like they take up volume, right? Like the drink in is at a cold temperature. So Celsius, like for the temperature, so it's like how you know like it's related to temperature, and then like think Celsius of the drink for the volume aspect of it. Um, then there's Avogadro's um law, which is like not to confuse with Avogadro's number, which is also named after the same guy, since there's not too many Avogadros in this world, or was, I guess, since he's dead. Um, so like think about it like the amount of gas. So, like the amount of gas that like occupies is the volume. So like Avogadro, like since like Avogadro is just kind of like synonymous with moles at this point, right? So it's going to be related to moles in some capacity. And then when you think of like amount of gas, it's like the volume of that gas that it's taking up. So like that's how you know that it's N1 over V1 equals N2 over V2. At least that's how I like to think about it. And then real quick, so like when you are talking about gases, it's kind of hard not to talk about like the different like boiling points, even though in ideal gases, you're assuming that they don't have any molecular interactions, which can be kind of confusing, but it's important to like make the distinction between the different boiling points. So ionic bonds are like just like molecule or ionic molecules, I guess I should say. They have like the complete octets, so they're like super satisfied, and it takes a lot of energy. So like if you're going back to like enthalpy, right? Like to break those bonds. Right? It's endothermic because you're breaking those bonds. They don't want to get broken. It takes a lot more energy just because it's like they have a satisfied octet, so they're not going to want to get broken up. Since if you break apart those molecules, then you won't have that octet anymore. Whereas if you have hydrogen bonding, I don't know, I did bonded, I don't know what that means. That's not a word. Hydrogen bonding, they have large electronegativity differences just because that hydrogen is just like so small, like so has such a small EN compared sorry, not EN. It has like such a different like EN compared to like hydrogen bonding. Also, like this is mnemonic I learned for it too. It's bond, right? So fluorine, oxygen, nitrogen, those are the three atom second hydrogen bonds. And that is just because it's like the such large electronegative differences, like it has large attractions. And then dipole, that's like the third most, like if you have like a boiling point and you're like comparing molecules, is permanent, but still like the electronegativity differences between the two. So like if you have like carbon and nitrogen, like it's still there. Like there's still going to be a permanent dipole, but it's not as prominent. Where and then you have like your London dispersion forces, and I like to think of it as like must have been the wind. It's like the induced dipole. It's just kind of like it's the weakest. Like all molecules have this, if that makes sense. So even like something that's like, like I don't know, like hydroxide, like that has London dispersion. It also has dipole dipole, but the like highest order it has is hydrogen bonding. So that's how I like to think about it. It's like kind of like that rectangle square debate. Um, that's how I like to think about it. It's like it encompasses all of it, and it's like the highest order of the hydroxide bond is hydrogen bonding, but it encompasses the ones that are below it. So like this would be below. So everything down. Um, yeah, so now let's talk about some common equations that you'll are associated with gases because there are quite a bit. We kind of covered the main one, which is the ideal gas law, which is PV equals nRT. But there also are some other ones that are just not as important, but they're pretty important. So like this, I would say is definitely like the most important of the sub ones, which is Dalton's partial pressure law. The other ones are kind of more theoretical. And there's two that I'll talk about that aren't super important, at least in my opinion, but it's just like you should still know them anyways, just to be a good um future doctor. Cover all your bases. So Dalton's partial pressure law, um, this is kind of saying like the whole is the sum of its parts. That's like a common theme in chemistry, is that like everything is like made up together, right? Like the parts of your body, it's like your hands are part of your body, like your arm is part of your body, and that's what makes up you. Same thing with atoms. Um, so if you have your total pressure, that's PT equals PA. So like PA is just like for gas A, and then plus the pressure of PB. So like that's what it is, and then like so on and so on and so on. My ellipses are there, which I don't know. Some people don't know what that is. That's what those three dots are. Fun fact. Um, and then another aspect of Dalton's partial pressure law is that your for gas A, that pressure of partial pressure of gas A is equal to the total pressure times the mole fraction. This isn't the number of moles. This is the mole fraction. So this number will always be um less than one. So it's never greater than one. If you see something that's like trying to trip you up, nah, it's a ratio, right? Ratios aren't like at least in this case, sometimes ratios can be obviously greater than one. But right, since you're doing dividing it by the end total, the sum, like the part can't be greater than the whole. Like that doesn't make sense for like your moles of A to be greater than the moles total because like you're adding it together, right? Like Na plus Nb is equal to N total. It's a sum. Um, so yeah, you're multiplying it together to get your partial pressure. So like you could think about it as like the fraction of the gas contributes to the total pressure too. So the more moles that your gas takes up, the greater a contributor it is. So yeah, it's pulling its full weight if it has a high mole fraction. Let's think about it like that. So this is going to be greater than like something that doesn't. Pulse weight. And then so we can talk about average kinetic energy next. So kinetic energy is equal to 3/2 over bolt sorry, not over, times Boltzmann constant times temperature. And this is always to remember like it's gonna be Kelvin, not Fahrenheit, not Celsius, but Kelvin. And then people are like looking at this and then like okay, this is like the standard equation for kinetic energy. It's like how the heck did that turn into that? How are these interchangeable? Um well, funny story. This one I can actually derive like pretty easily from math, but the other equations that we'll see, I can't. So for gases, you're assuming this is kind of more a theoretical thing is too. It's like nice to think about. So like for gases, you're assuming that the kinetic energy is uniform throughout all the particles. So like that's another thing. So like temperature, when you look at a thermometer and you're like, oh my God, it's so hot. It's like 90 degrees. I'm in the US, so we use Fahrenheit, unlike the rest of the world. Um, but yeah, so like when you look at temperature, it's like the average kinetic energy. When you see like that thermometer, it's like all those particles in the air, all the air, oxygen, nitrogen, that's in the air. It's the average kinetic energy, hence the temperature. So those are like proportion, um, like they're directly related to each other. Like that's how temperature is measured. Um, so like that's where the T came from in that equation. And then there are three dimensions, right? So like if you're like looking at yourself in space, right? You're not 2D, you're not like a Disney princess, unfortunately. And you're not 1D, like you're not just a line. You're 3D. It's like so like there's three dimensions. So you have X, Y, and Z. So like three is gonna because like the energy in gases, as we already said, is spread equally across like the whole particle. So it's like I can't draw anything that's 3D, so but imagine this is like a sphere. I guess. Oh my gosh. Yeah, no, I'm not even gonna try. So imagine there's like a sphere, right? It's spread equally across like the whole surface of the sphere, or like across the sphere. Hence the three, which is in the numerator, the three halves. So you're still keeping the one half, but like the three is in the numerator, since like compared to like other aspects of like when you're comparing like kinetic energy, not gas particles, it's just like it's not equally spread out. So that's why it has that one like monodirectional thing. So like usually kinetic energy is monodirectional, which is where that one came from in the numerator. So one per half, please. Here, sparks fly. Instead of one. So that's where that three halves came from. Okay, and the last one is Boltzmann's constant. And this is a little bit harder. So Boltzmann's constant, this will most likely be given to you on MCAT. But you could also memorize it just in case. But it's a little mean for the test makers to expect you to remember like this like really like random um like piece of information. So it's 1.38 times 10 to negative 23 joules per Kelvin. And this is kind of the bridge between the macroscopic world. So like when you're looking at I don't know, like yourself, like it's like stuff that you can see, right? And like the microscopic measures. Um, since it is like the MV squared portion, here I should use a different color. So it is the MV squared portion of the so MV squared portion, sorry, of the kinetic energy, like just like the plain old kinetic energy equation. So it converts the energy of the integer of the individual particle to a temperature. Hence the Kelvin in the bottom. And then joules is just like the it's energy, right? Joules is always associated with energy. That's like another common thing to keep in mind. Um, Okay, so then we have the heat capacity at constant volume, and then you have the heat capacity at constant pressure. So at constant volume, it's CV equals 3 half over, sorry, not over, times moles times the R constant. And then heat capacity at constant pressure is 5 half times moles times R. And it's way too mathematically complicated to explain the equations. I don't really understand where the equations came from. They're like, it's way over my head. My teacher probably tried to explain it to me in the past, but I'm like, just zoning out. But kind of how you can remember like the differences, like that three half, right? Like, it came from, it's like the same reason that we have like the three half for the average kinetic energy equation, right? Like Boltzmann's constant and stuff. Because it's like gases are like it's spread across like equally throughout the gas particle. So that's where the three half came from for the heat capacity. And also like how you can remember that like the heat capacity at constant pressure is larger, like it has that five half instead of like the three half is that like at constant volume, like you can't do work. So like that's always going to be like smaller than something that can't do work. Like there's going to be like less energy involved. Than something that's at constant pressure. Since if you're at constant pressure, you can do work. Yay, huzzah. Um, and then I guess like just remember like the three half versus the five half. So you're just adding like a whole like I guess like one to it, I guess so, right? Since this is a one half. So you're adding two out of two. So you're adding a five half in order to you're just adding like one equivalent to it, right? Since like you have to like keep the denominator the same. Otherwise, since you can't just add one over one, you have to multiply it times two in order to get to the two, right? It's the same thing, but you just have to add it there. Hopefully that made sense. I'm like rambling a little bit. These aren't really as like useful, I guess, but they can still show up. Like I would say this is like really low yield. But yeah, I feel like that's kind of it about what gases are like. Hopefully that made sense. Thank you for listening to my whole video if you actually did make it to the end. Um, and yeah, have a good rest of your day. Bye.